Have you ever wondered how you measure a movement that's super, super tiny but with absolute precision? Well, today we're going to pull back the curtain on the device that does exactly that, the LVDT. It's a fantastic little sensor that turns physical motion into a really clean, precise electrical signal. Let's dig in and see how it works.
So you look at these and yeah, they just look like a bunch of metal rods, right? Nothing too exciting, but don't let that simple appearance fool you. These are Linear Variable Differential Transformers, or LVDTs for short. And believe it or not, they are some of the most reliable and accurate sensors you can find anywhere, used in everything from the deep sea all the way to outer space.
All right, here's our game plan. First, we'll get a handle on what an LVDT actually is. Then we're going to crack one open, figuratively, to see its components. After that, we'll get into how it actually works, learn to read its signal, and finally, we'll see why these things are pretty much everywhere. Okay, first things first. What exactly is an LVDT? Well, its whole job is to be a kind of translator. It builds a bridge between the physical world of things moving and the electrical world of signals. You know, the name actually tells you everything you need to know. It's a transformer that deals with linear or straight-line movement. Variable just means its output changes depending on the position. And differential, that's the real secret sauce, and we'll get to that in just a second. So the main takeaway is this: it's a device that gives you a voltage that perfectly matches a physical movement.
To really get how it does this, we need to pop the hood and take a look inside. The real genius of the LVDT is just how simple and elegant its design is.
Take a look at this cutaway view. The first thing you probably notice is, well, how little is actually in there. You've got the outer housing, and inside, just a few coils of wire and a little rod that moves back and forth. There are no parts grinding against each other, and that lack of mechanical contact is exactly what makes the LVDT so incredibly durable.
So let's break it down. You've really only got three key players. Right in the middle is the primary coil. That's where we feed in the electricity. Then you've got two identical secondary coils sitting on either side of it. And the last piece of the puzzle is the movable core. It's just a small rod made of a special magnetic material, and it slides friction-free right through the center of all those coils. This is the part that you'd attach to whatever it is you're trying to measure.
So we have our three parts. How in the world do they work together to measure something? Well, it all comes down to the magic of magnetic fields and a cool physics principle called mutual induction. Okay, here's the play-by-play. We sent an AC voltage into that primary coil in the center. This creates a pulsing magnetic field around it. That magnetic field then expands out and, thanks to mutual induction, creates a voltage in both of the secondary coils. Now that movable core, its whole job is to act like a guide, channeling more of that magnetic energy to one side or the other, all depending on its position. And this right here brings us back to that word differential. The LVDT doesn't actually care about the total voltage in each secondary coil. What it measures is the difference between them. They're wired up in such a way that their voltages subtract from each other. And this design is absolutely brilliant because it cancels out all sorts of electrical noise and temperature changes, giving you an incredibly clean and stable signal. And this shows it perfectly. When that core is sitting dead center, it's sending the exact same amount of magnetic energy to both secondary coils. So they produce identical voltages, V1 and V2. But since they're wired to oppose each other, they completely cancel out. The final output, as you can see in the graph on the right, is a flat line, 0 volts. We call this the null position. But the moment that core moves, even a tiny bit, that perfect balance is broken. If it slides toward one coil, that coil gets more magnetic energy, and its voltage goes up. The other coil gets less, so its voltage goes down. Now, when you subtract one from the other, you don't get 0 anymore. You get a measurable voltage that is perfectly proportional to how far the core has moved. Okay, so we've got an output voltage, but what is that signal actually telling us? Let's take a look at how to decode the LVDT's language to get some real useful information. This V-shaped graph is basically the LVDT's signature move. Along the bottom, the horizontal axis, you have the core's position, with 0 right in the middle at that null point. The vertical axis is the output voltage, and you can see it plain as day. The farther the core moves from the center, in either direction, the higher the voltage gets. And just look at how straight those lines are. That's what engineers call excellent linearity, and they love it. So the beautiful thing here is that this one signal actually gives us two different pieces of information. The magnitude, or just how big the voltage is, that tells us how far the core has moved, and the phase of the signal, basically whether it's in sync with the input or not, tells us which direction it moved.
It's just a super efficient way to capture both distance and direction.
Now, this clever and simple design gives the LVDT some serious advantages. And that explains why it has become the go-to sensor in so many demanding industries.
I mean, think about it. With no physical contact between the core and the coils, there's no friction and no wear. That means it has a practically infinite lifespan. It also means it can detect ridiculously small movements, what we call infinite resolution. On top of that, these things are tough as nails. They can handle dust, moisture, and heavy vibrations and still give you a highly sensitive reading.
So when you combine that kind of precision with that level of toughness, you get a sensor that engineers trust for the really important mission-critical jobs. You'll find them in factory automation, making sure everything is perfect. They're in airplanes controlling flight surfaces, in robots for exact positioning, and even in civil engineering where they monitor the health of bridges and buildings.
So the LVDT really is a perfect example of elegant engineering. It takes a simple principle, magnetic fields, and uses it to create a sensor that's both incredibly precise and almost indestructible. Now that you know its secret, where do you think you might find this technology at work, hiding in plain sight all around us?